A modern commercial vessel relies on a single, continuous mechanical chain to maintain heading against thousands of tons of ocean force. If the steering gear fails, the ship immediately becomes an unguided projectile. To eliminate that risk, international maritime law sets a rigid baseline for vessel construction. The primary directive is Regulation 29. At the core of this regulation is the single failure criterion. The law mandates that no isolated mechanical, electrical, or hydraulic fault in the steering system can render the ship unsteerable. We are going to mentally engineer a fully compliant steering architecture from the ground up, relying purely on the strict logic dictated by this text. We will start by mapping the raw hydrodynamic loads acting on the hull, then move up through the internal hydraulics, and finish with the autonomous logic gates required for high-risk vessels. Regulation 29 functions as a complex mathematical and structural puzzle. Naval architects solve it to guarantee that a vessel can survive severe hardware trauma without losing control. Before introducing any redundancy, we have to establish the sheer physical capacity required. A steering mechanism must actuate a multi-ton rudder against extreme water resistance while the vessel travels at maximum velocity. Regulation 29, paragraph 3.2, defines the absolute baseline performance mandate for the main steering gear. This 3D wireframe illustrates the strict metric. The main gear must rotate the rudder from 35 degrees on one side to 30 degrees on the opposite side in no more than 28 seconds. That maneuver must be achievable under the highest stress conditions possible, with the ship sitting at its deepest seagoing draft and running at maximum ahead service speed. This creates an immediate problem during early construction. It is frequently impossible to fully load a ship to its deepest draft for a test run during initial sea trials. Paragraph 3.2.2 offers a precise mathematical workaround to verify the machinery without the heavy cargo. Naval architects isolate the specific submerged rudder blade area achieved during the light trial condition. They use this area, combined with the ship's continuous engine revolutions, to calculate the expected hydrodynamic torque. This equation is then projected onto an extrapolated torque curve. By matching the predicted force against the trial data, they artificially simulate the physical strain of the full load condition. Once the main gear clears this threshold, paragraph 4.2 enforces a secondary requirement for the auxiliary steering gear. The auxiliary system has its own distinct timing metric. It must swing the rudder from 15 degrees to 15 degrees in no more than 60 seconds. The operational load conditions for this backup test are slightly reduced, running ahead at either half of the maximum service speed, or 7 knots, whichever is greater. Proving these baseline timings ensures the vessel possesses a mathematically guaranteed threshold of brute force maneuverability. Only after establishing this capacity does the law demand redundancy. Generating that level of external force requires extreme internal hydraulic pressure. The regulatory focus shifts from the water outside to the fluids inside. Paragraph 2.2 dictates a strict design pressure mandate for all internal piping. In this schematic, the hydraulic piping scantlings are calculated to withstand a massive margin of error. The system must tolerate at least 1.25 times the expected maximum working pressure. To guarantee the system never breaches this limit from an unexpected external wave strike, mandatory relief valves are integrated. To prevent total loss of pressure from a single pump failure, paragraph 6.1 enforces a redundancy mandate for the power units themselves. Architects can meet this by either completely separating the main and auxiliary systems, or by building the main steering gear with two identical, entirely independent power units operating in tandem. But fluid power is only as resilient as the logic determining where it flows. We have to address the electrical control pathways. Paragraphs 8.1 and 9 explicitly acknowledge that dual hydraulic pumps are useless if their electrical instructions rely on a shared wire. The law requires that all electrical control logic must originate from completely dedicated circuits, pulling power directly off the main switchboard. Furthermore, these redundant cables cannot run side by side. They must be physically separated throughout their entire length across the ship, ensuring a single fire or collision cannot sever both lines. Raw mechanical torque is effectively blind. The architecture demands that both the high-pressure fluid buffers and the delicate electrical logic pathways remain strictly isolated to guarantee the signal reaches the rudder. For chemical tankers and gas carriers exceeding 10,000 gross tonnage, the stakes scale up drastically. Because of the high-risk cargo, the administration deems standard separated redundancy entirely insufficient for these massive holes. Consider the absolute worst-case failure. A major hydraulic pipe bursts under extreme pressure while the vessel is transiting at maximum ahead service speed. Paragraph 16.1 introduces a uniquely demanding performance standard, the 45-second rule. This dual-system circuit highlights the mandate. Following a catastrophic single failure in the power actuating system, full steering capability must be completely regained in exactly 45 seconds. Human reaction time is too slow to meet this window. The interconnected hydraulic systems are heavily automated, featuring immediate fluid loss detection that triggers shutoff valves to lock out the ruptured section. Once sealed, the system autonomously reroutes the fluid pressure entirely through the intact actuators, salvaging the surviving machinery without manual intervention. Surviving the pipe burst is only half the problem. Paragraph 14 demands an independent backup power supply. This electrical source must detect the failure and automatically sequence online within that same 45-second window, driving the surviving hydraulic loop. The only accepted single points of failure in this entire sequence are heavy static mechanical components, like the main tiller or quadrant, which are engineered with massive safety factors. By integrating sensors, automated control valves, and backup power grids, the regulation forces the steering gear aboard high-risk vessels to evolve into an active, self-healing autonomous network. When we combine all the stipulations of Regulation 29, the full architecture reveals its density. The foundation demands guaranteed brute force, measured by strict 28-second and 60-second actuation timings under heavy load. The structural layer builds internal buffers through 1.25 times overpressurization margins and targeted relief valves. The control layer mandates absolute physical and electrical segregation, isolating logic cables from the main switchboard all the way back to the steering compartment. And the final fail-safe layer forces the largest tankers to execute an interconnected, autonomous fluid recovery in 45 seconds or less. The law does not allow naval architects to assume normal operating conditions. It forces them to specifically design for the most violent, debilitating equipment failures possible. Every redundant pump and separated wire guarantees that a localized rupture can never cascade into a total loss of navigation. Regulation 29 provides a comprehensive defense against mechanical entropy. It ensures that even when a critical component fails, the vessel retains absolute control in the ocean's most unforgiving environments.